So far we've only talked about carbon being hybridized. In this video we're going to see that atoms other than carbon can also be hybridized, and we're going to analyze everything using something called the steric number, and we're also going to figure out the overall geometry of the molecule. So to calculate the steric number, what you do is you add the number of sigma bonds that are around an atom, and to that, you add the number of lone pairs of electrons that you see around that atom. And this gives you the steric number. The steric number tells you some very important information. It tells you how many hybridized orbitals that you have. And the number of hybridized orbitals that you have is going to help you to figure out the overall geometry of the molecule. For example, when the steric number is equal to 4, that means you have 4 hybridized orbitals. In the video on sp3 hybridization, we saw that the way to get 4 hybridized orbitals is to take one s orbital and 3 p orbitals, hybridize them together, and you get 4 sp3 hybrid orbitals. So therefore, whenever the steric number is equal to 4, the atom is going to be sp3 hybridized. So if we look at the methane molecule, right, just draw a carbon in there to refresh your memory, and I wanted to calculate the steric number for this carbon. Right, so our goal is to calculate the steric number for this carbon. The steric number is equal to the number of sigma bonds that surround that carbon. So those would be our single bonds here. So 1, 2, 3, and 4. So 4 sigma bonds plus the number of lone pairs of electrons around that carbon. In this case, it's 0. So 4 plus 0 is, of course, equal to 4. So the steric number is equal to 4. That carbon is sp3 hybridized, which we knew already from an earlier video. In terms of the geometry of this, all right, since that carbon is sp3 hybridized, those electrons in blue are going to repel each other. So they're going to try to be as far away from each other as they possibly can, according to VSEPR theory, valence shell electron pair repulsion. Right, since electrons are all negatively charged, they're going to repel each other and give you this shape, this geometry around your central carbon atom. So we called this geometry tetrahedral in an earlier video, and there's also a video showing you where the bond angle comes from. So all the bond angles for methane turn out to be approximately 109.5 degrees, like that. Let's do the same thing for the ammonia molecule down here. Let's analyze the hybridization of the central nitrogen atom here. So if I wanted to calculate the steric number, right, I would take the number of sigma bonds. So that would be 1, 2, and 3. So 3 plus the number of lone pairs of electrons around that atom. So 1 lone pair of electrons. So 3 plus 1 is equal to 4. Steric number 4 tells me I need 4 hybridized orbitals, so this nitrogen is sp3 hybridized. So we have an sp3 hybridized nitrogen, and when we look at the shape of the ammonia molecule, so we're going to have nitrogen in the center here, and then we're going to have our hydrogens coming off of the nitrogen like that, and then we have a lone pair of electrons, right, in an sp3 hybridized orbital like that. So we have this situation. So it looks a lot like the ammonia molecule. The difference is now instead of bonding electrons like in the methane molecule, I should have said, we have non-bonding electrons, and these non-bonding electrons, this lone pair of electrons, are going to repel these bonding electrons a little bit more than in the methane example. And so we're not going to see a bond angle of 109.5. It's going to be a little bit smaller than that. So this bond angle turns out to be approximately 107 degrees. In determining the geometry of the molecule, the geometry of the atoms around the nitrogen molecule, we ignore the lone pair of electrons, and we just and if we do that, we can see a little bit of a pyramid shape. So this is called trigonal pyramidal, right? So trigonal because nitrogen's attached to 3 atoms, and pyramidal because it looks a little bit like a pyramid if you ignore the lone pair of electrons. So that takes care of the ammonia molecule. Let's now look at the water molecule. All right, and our goal this time is to calculate is to find the hybridization state of this oxygen. So the way to do it is to use the steric number, right? So steric number is equal to how many sigma bonds do we have? We have 2 sigma bonds for this example. How many lone pairs of electrons? We have 2 lone pairs of electrons. So 2 plus 2 gives us 4. Steric number 4 means that oxygen is sp3 hybridized. And so I know I know the oxygen is sp3 hybridized, and the lone pairs of electrons occupy occupy sp3 hybridized orbitals. The difference here is I have two lone pairs of electrons, and so those non-bonding electrons are going to repel these bonding electrons even more than what we saw in the previous example. And so the bond angle isn't going to be 109.5, it's not going to be 100.7, it's going to be even smaller than that. So it turns out that this goes down to approximately 105 degrees here. So 105 degrees for the bond angle in a water molecule. When I think about the geometry, once again we ignore the lone pairs of electrons and just focus in on the bonds. And so we can see that this looks kind of like an angle, right? So you could call this angular, or you could say that this is bent. So the geometry is described as either bent or angular for this example. Let's move now to situations where the steric number is equal to 3. So if the steric number is equal to 3, that means that means you have 3 hybridized orbitals. And in the video on sp2 hybridization, we saw how to make 3 hybrid orbitals. We took 1 s orbital and 2 p orbitals, which hybridized to give us 3 sp2 hybridized orbitals. And so let's look at the ethene molecule. Right? So we saw this molecule in the video on sp2 hybridization. But let's go ahead and calculate the steric number for the carbon on the right. So if I wanted to find the steric number for the carbon on the right, I would take the number of sigma bonds. So let's see, here's a sigma bond, here's another one. And the double bond between my two carbons, I know one of those bonds is a sigma bond, right? The other one's a pi bond. So I have 3 sigma bonds, and to that the number of lone pairs of electrons around the carbon, which is of course 0. So 3 plus 0 gives me a steric number of 3, so I know that this carbon is sp2 hybridized. So if I wanted to draw a picture of this ethene molecule, the carbon on the right is sp2 hybridized. The carbon on the left is exactly the same, so it's also sp2 hybridized. And so let me go ahead and sketch in the sigma bonds that form, right, from those sp2 hybrid orbitals, which we discussed in the earlier video there. So since these carbons are sp2 hybridized, there's an unhybridized p orbital. So we can go ahead and sketch in the unhybridized p orbital like that. And the side-by-side overlap creates the pi bond that we see. So that would represent the pi bond right here in the dot structure on the left. So when we think about the geometry for a carbon that's sp2 hybridized, what's the geometry of the atoms around an sp2 hybridized carbon? So this we've seen these angles must be 120 degrees, right? 120 degrees implying that's 360 degrees divided by 3, meaning it's planar, right? So the atoms are arranged in a planar fashion. So since each carbon is sp2 hybridized, right, this is a trigonal planar geometry, right? So let me go ahead and write this: trigonal planar geometry for the atoms around an sp2 hybridized carbon, in this case, giving us a bond angle of 120 degrees. When I look here at the pyridine molecule, right, these are carbons all the way around here like that, and then there's hydrogens attached to all of these carbons. Let's figure out the hybridization of the nitrogen atom in the pyridine molecule. So I'm trying to calculate the steric number for this nitrogen. So the steric number would be equal to number of sigma bonds. So here's one sigma bond. Here I have another double bond. Right, so one of those is going to be a sigma bond, and one of those is going to be a pi bond. Right, so I have a total of 2 sigma bonds, and this time I have 1 lone pair of electrons. So 2 plus 1 gives me a steric number of 3, which means that this nitrogen must be sp2 hybridized. So if the nitrogen's sp2 hybridized, let's go ahead and sketch it out here. The nitrogen's sp2 hybridized. Those single bonds form from sp2 hybrid orbitals of the nitrogen, and then there's another sp2 hybrid orbital from the nitrogen that's going to contain the lone pair of electrons, and so that's what I'm going at. This lone pair of electrons occupies an sp2 hybridized orbital. Now, since nitrogen's sp2 hybridized, that must mean it has a p orbital as well. So I'm going to go ahead and sketch in a p orbital in here on the nitrogen. And if I wanted to calculate the steric number for this carbon, right, I know that it would be 3. It's just like the previous example. So that carbon is also sp2 hybridized. So I'm going to say that that carbon is represented right here. And since that carbon's sp2 hybridized, it's going to have a p orbital like that. And so we can see that that's the pi bond between the carbon and the nitrogen. So here's the pi pi bond between the carbon and the nitrogen. So these two electrons here are in a pi bond, right? So the electrons in magenta do not occupy an sp2 hybridized orbital. All right, let's do one more example, and of course this is where your steric number is equal to 2. And let me just real quickly talk about the geometry of the nitrogen atom that we just discussed up here, right? So the nitrogen, right? If we ignore the lone pair of electrons, it would look like this, and that of course looks bent, right? So that we could say that this geometry here is bent. So you have to think about the hybridization of the atom, and you have to think about lone pairs of electrons, right? When you're trying to figure out your overall situation here, and when for this you ignore the lone pair of electrons when you're determining the geometry. All right, our final example, steric number is equal to 2. That means you have 2 hybridized orbitals. You can make 2 hybridized orbitals from one s orbital and one p orbital. So therefore, when the steric number is 2, we're talking about an sp hybridized atom. So this example, right, acetylene, here are my 2 carbons like that. So if I wanted to calculate the steric number for, let's say, the carbon on the right, steric number is equal to number of sigma bonds connected to that atom. Here's one sigma bond and a triple bond. Remember, one of these is a sigma bond, the other 2 are pi bonds. So the steric number would be equal to 2 plus 0, no lone pairs of electrons around that carbon. So we have a steric number of 2, meaning 2 hybrid orbitals, meaning sp hybridization. And so that carbon is sp hybridized. Right, this carbon over here is also sp hybridized, and in terms of the bond angle, right, this would give us a straight line, and so the bond angle is 180 degrees, and the geometry we would say the geometry is linear, right? So let me just erase that really fast. We have linear geometry. So calculate the steric number of these atoms, figure out the hybridization, look at the lone pairs of electrons, and then you can figure out the overall geometry of all the molecules in an organic chemistry course.